Alright, in this video we want to solve the inverse Laplace transform of the given functions of a's. So from the first question we see that we have to find the inverse Laplace transform of a's plus 2 over a squared plus 4. Alright, believe you know Laplace transform of some functions, okay, transforming from the function of t to function of a's. So we're just gonna take this as an inverse, okay, just backwardly. You are given this, then you take it back to its original function. So we reduce it to a certain point, then your ability to recognize the Laplace transform of which function will give you this particular function, okay, of a's. So the Laplace inverse of this function will give you that original function. Let's take it in terms of t. Alright, okay, so the manipulation here is just to rewrite this in a form that we can recognize it. Alright, so I'm going to rewrite that as I'm going to split this into two fractions. The first being a's over a squared plus 4, alright, and I add it with 2 over a squared plus 4. Okay, so let's continue from here. Alright, so the next thing I would like to do here is to go ahead and recall a property that the Laplace inverse or the Laplace transform any one of the sum is the sum of the Laplace transforms. So I'm going to go ahead and take the Laplace inverse of the first one, that is a's over a squared plus 4, alright, plus the Laplace inverse of the next thing we have 2 over a squared plus 4. Alright, now here is going to be very simple. Alright, we know that when we take the Laplace transform of a cosine of let's say at, just as a reminder, this gives us a's over a squared plus a squared. Alright, so we'll be looking at this. This is a's on top, very nice. In fact, why will I even so I'm just recalling this because this is what we're gonna get, okay, something of this form. We know that a's is here and is here, so a square is here and a square is here. Here we just need to get a square, and good enough, this is just a perfect square already. Okay, 4 is a perfect square. So which number are we going to square to have 4? We have 2 to square, so that means a here must be 2, such that 2 square will give us 4. Alright, so knowing that, let me just clean that. So this must be cosine of a here is going to be 2, such that 2 square will give us 4. So cosine of 2t. Alright, that is it for the first part. And for the second part, well, I'll also remind you that when we have the Laplace transform of sine of at, this gives us a over a squared plus a squared, like that. Alright, so we're just going to apply that right here. And you see on top here we just have 2, and here is just 4, which is gotten from 2 squares. Alright, so that is just it. This is just sine. So you can write that as sine of 2t, and that is it for the first question. It's very simple. Cosine of 2t plus sine 2t. Okay, let's move on to the second question. Okay, so here we have to take the Laplace inverse of 2 over a squared plus 3. Well, this is just going to be straightforward, but we're going to have to do some things for it, okay? Okay, in the previous question, we got to a point where I had to remind you that when we take the Laplace transform of sine of at, okay, we get a over a squared plus a squared. Now, since this is just 2 here, and this is a squared, I want to get that form, right? So we need to get an a such that when we square it, we get it at this point, and when we don't square it, just a normal a, we get it at the top. Alright, so since this is 3, it means that 3 is gotten from a square of something, okay, a square of something, so that thing must be square root of 3. Let me put it down. So that thing must be square root of 3. Alright, so that when we square it, we just get 3 right here. Okay, and since a square is on the denominator added with a square, and the a itself is on the top, so this place must be square root of 3. So I would like to go ahead and apply that immediately, and also let you know that when we see the Laplace transform or Laplace inverse, anyone, of a constant multiplying with t, okay, and where t is the variable and a is just a constant, is the same thing as a times the Laplace transform of t. Alright, so when the constant multiple, we just take it out like that. Okay, so that's pretty simple. So let me just apply that right here. So I'm going to move these two to the front, so we're going to get something nice. Okay, so from here we're going to have the Laplace inverse of 2 over a squared plus, now this 3, I can write it as square root of 3, and now square that. Okay, then I will take the 2 to the front, like I said, 2 times the Laplace inverse of 1 over a squared plus square root of 3 square, and that is it. Alright, well, the next thing I would like to do here is to multiply this, right, with square root of 3 and divide it by the square root of 3. Alright, so this will now become 2 times the Laplace inverse of, so I said multiply the top by square root of 3. Let me use something for that. Square root of 3, alright, and the denominator also by square root of 3. So here we're going to have a square plus square root of 3 square. So what I just did there is to multiply by something and divide by the same thing, top and bottom, so the thing will just cancel out. It's just the same way. Okay, I'm just putting this so that it will help us. So since we need the square root of 3 at the top, this one at the bottom, 1 over square root of 3, I can just take it out, and finally we will enter with 2 over the square root of 3 at the bottom. Alright, then I take the Laplace inverse or the inverse Laplace transform, anyhow you choose to position it, of square root of 3 divided by a square plus square root of 3 squared. Alright, okay, so let me just put down the final thing for us to see. I will have to clean this part immediately. We will see now that that is equivalent to sine of some function. Okay, so I'll write it down as 2 over square root of 3. Then the Laplace inverse of this is just sine of, in place of a, we're having a square here, we're having a here, that will just be root 3t, and that right there is the solution to the second question. Okay, thanks for watching.